So the next talk is titled On the Impossibility of Game-Theoretically Fair Leader Election Protocols, authored by Ohad Klein, Chenzi Zhu, and myself. And the speaker is Chenzi.
So, hello everyone, thanks for the introduction. So let's say Alice, Bob, and Eve, they have a paper accepted at TCC, and they all of them want to present the paper. So they need to run a leader election protocol to decide who will present the paper. And here we assume the existence of broadcast channels, so there's no agreement issues. And ideally, we want the outcome to be uniformly distributed among them, even if a coalition or party can collude and deviate from the protocol. So in particular, we're interested in a setting where the size of a coalition is more than 1/2. So for two-party setting, this is essentially the coin tossing problem. And unfortunately, it is hard to do coin tossing in the presence of a malicious majority. So more precisely, it is impossible in the information theoretic setting, and the famous Cleve's lower bound shows that it requires high round complexity to achieve the strong unbiased guarantee. So to bypass this Cleve's lower bound, the good news is that we don't need strong unbiased notions for the problem of Alice, Bob, and Eve. And as observed by Blum in early 80s, a weaker notion referred to as game theoretic fairness is enough. And the recent line of work has shown it's possible to construct efficient multi-party leader election protocol satisfying this notion. And this notion is first formalized for multi-party protocols by Chang et al. In 2018. And it guarantees a coalition of malicious parties cannot harm honest parties' utility, nor can they increase their own utility. Where here the utility refers to the probability of being elected. So we call the former maximum fairness and later CSP fairness. So to see this notion is easier to achieve, a simple example is Blum's coin tossing protocol, which is perfectly game theoretic fair. So for two-party, Alice and Bob. So in the first round, each party samples the random bits, and they commits the bits to each other. And in the second round, they open the bits. So if no party aborts, then the leader is decided by the XOR of two bits. And if one of the party aborts, the leader becomes the other party. So it is now hard to see that this protocol is perfectly fair. So suppose the Bob is malicious. And the first, it should not abort because there's no benefit of doing it. And if Bob does not abort, and he cannot see the Alice inputs when he decides his own inputs. So the probability that Alice will win will be at least 1/2, which implies the protocol is perfectly fair. But however, this protocol is not unbiased because the Bob could always make the protocol output 0 by just aborting. So what we know so far about the game theoretic fair leader election protocols. So here, let's see the following diagram where the x-axis is the coalition size and the y-axis is the round complexity. So here the n denotes the numbers of parties. So for maximum corruptions, we can extend the prior Blum two-party protocols to n-party settings. And this will give us the folklore tournament tree protocols. And it achieves perfect fairness, and it requires log-in rounds. And for slightly less coalition size, Chang et al. Proposed a log-log room protocol that has achieved approximate fairness against a coalition of size n minus n over log-in. And it also offers further trade-off when the size of coalition is less than n minus n to the epsilon. And later, Komargodski et al. Proposed a log star and round protocol when only a constant fraction of parties collude. And they also offer further trade-off up to the size of coalition of n minus n over log-log-n. And in terms of lower bounds, we know that it is still impossible in the information theoretic setting. and also one-way function are necessary. However, the only other lower bound we know is proposed by Cham, where they consider a special class of protocol called the commit and reviewer protocols, which I will explain later. And they show this log n run is tied for perfect fairness against n-1 correlation. So we can see that in terms of lower bound, basically we know nothing in the case where the numbers of parties is less than n-1, or when we do not require perfect fairness. So in this work, we also consider this commit and review protocols, and we show that log n over log n round are necessary for achieving approximate fairness against a correlation of size more than n minus n to the epsilon, and we also show further trade-off. Concretely, the trade-off is as follows. And furthermore, for perfect fairness, we show the log n rounds are necessary against a correlation of size n to the epsilon, and also is a further trade-off. We also highlight that for single round protocols, we give concrete bounds on how fair they can be, and also show this bound is tight. So for the rest of talk, I will mainly focus on our result on approximate fairness and try to give some our proof ideas. So before that, we'll first explain what are the commit and review protocols. So this protocol are of the following special form, where in each round consists of two phases. A commitment phase where each party samples a random input from a domain omega, and they broadcast a commitment of the input to each parties. And an open phase where the parties just open its input. And if a party I aborts at round j, we set the input j, xji to be abort. And then an R round n party commit and review leader election protocol can be represented by a function which takes the inputs from all parties across all rounds and outputs an index that indicates the leader. And here are several examples of this class. So, and also for approximate fairness, I will also only give the formal definition for maximum fairness here, since it will be the focus for the rest of the talk. So for any protocol pi, we say it is 1 minus epsilon maximum fair against correlation of size k. If and only if for any correlation of size k and any strategy of S, the probability of any honest party that is selected will be at least 1 minus epsilon over n, where all parties not in S act honestly. And intuitively, it means so a protocol satisfies that any honest party wins with at least probability alpha is equivalent to say that it's alpha times n maximum fair. So for single round protocol, we show the following theorem. So for simplicity, we only consider n-1 correlations for this talk. And to prove the theorem, let's take the three-party case as an example. So suppose party 1 and 2 are corrupted. And the goal is to make the probability that party 3 being elected to be as small as possible. And due to the commit and review property, we know that the bad party cannot decide their input depending on the input of party 3, but they can decide whether to abort after party 3 open its input. So the idea is we can let one of the bad party abort if it will make the party 3 not be selected. So we denote the event Wi as a party 3 is elected if I aborts. And intuitively, if the party, given the party 2 aborts, and there should be a fair competition between party 1 and party 3. So the probability that the W2 occurs should be at most 1/2. And similarly, the probability that W1 occurs should be at most 1/2. But then the probability that the party 3 is selected will be bounded by the probability that both W1 and W2 occurs. Because if one of the event does not occur, for example, if W1 is not occurred, It means that we can let party 1 abort to make the party 3 not be elected. And if these two events are independent, then we can show this party 3 is elected with at most a quarter. And this will basically show of a lower bound. And this argument is not formal, and there are several issues we need to fix, but because the limit of this talk, I refer to the paper for the fault proof. And we also give a concrete construction that matches this lower bound. So the idea is we can let each pairs of party run the Bloom's two-party protocol, and the party is elected if it wins all its matches. And if no such a party exists, then an arbitrary party is selected. You can see for any honest party, the probability that they win in one of the matches is at least 1/2. So the probability that it wins both matches is at least 1/4. So which matches our lower bound. And we also extend our results to committee election protocol, where the goal is to output a set of party with a specified size instead of a single party. And finally, I will try to give a proof sketch for the multi-round result. So given a R-round and party protocol that satisfies the alpha maximum fair, so let's consider after the first round of committee review, we say the party I is eliminated if the probability that I is elected will be slightly decreased. And if we can show that there exists a first round execution, that the numbers of party will be remains will be larger than n over log n, then we can show that we can derive an R-1 round protocol for n over log n parties that is achieve relatively the same fairness guarantee. So intuitively, this means that after each round of protocol, there are some party might be eliminated, but the speed it decrease is at most by log n. So it means at least need log n over log n rounds for the numbers of party to be reduced to 1. And lastly, to show this lemma, suppose that for any first round inputs, the remaining party is bounded by n over log n. And then we can view the first round of the protocol to be a single round n party committee election protocol that select a committee of size n over log n. And where the remaining party are the selected committee. And we can show this protocol is one of n maximum fair, which contradicts our lower bounds of single round protocols. And finally, I will end my talk with several open problems. The first is, can we extend our results for general protocols? And the second is, our lower bounds on the approximate fairness only covers the case where the size of collision is almost n. So it will be interesting to see whether we can prove something for smaller collision size. And the third is interested to see whether our lower bounds are tight. And yeah, that's all for my talk. Thank you.
Questions?